Thank you for the invite. Yeah, I thought I was going to speak about some more recent progress, but progress has been slow. So I'll be giving a talk about something that's already up on the archive. And maybe if there are questions, then I can say something more. But so some of you might have heard a version of this talk. So in that case, maybe some of this is already familiar, but yeah. But just to keep up with the ever-changing topics on the seminar, I'll first start with a short review of instant-on flow theory and then move on to the main result. Yeah. So, so instant-on flow theory is about the Chern-Simons functional and doing Morse theory with it. So, just as a brief reminder, your critical points of the Chern-Simons functional are homomorphisms from pi 1 of y, say, where y is your three manifold, where you look at SU2 representations up to conjugation, and you'd like to do Morse theory on this. And on the cylinder R cross Y, you count AHD solutions. Now, we won't exactly be using this version for the talk today. We'll instead essentially just kill the conjugation action and be looking at directly homomorphisms from either your three manifold to SU2 or the knot complement. And we'll get to that in a little bit. But the notation for this is I sharp of y comma L if there's a link, and the it's supposed to be substitute for the homology of your representation variety, and this representation variety is you're looking at rho belonging to form of, say, the knot or the link complement, and you're looking at SU2 representations, and you ask for rho to send all the meridians to a traceless element of SU2. Yeah. So remember that there's an S2 sitting inside SU2, which corresponds to traceless elements. And this is the character variety of interest for us. Note that we're not modding out by conjugation here. Yeah. And this is defined for any closed-oriented three-manifold and any link. The link could be empty, in which case this condition is always satisfied. So you just look at SU2 representations from your fundamental group of your three-manifold to SU2. And yeah, and you can have as many components as you want. Okay. And I want to just go over some properties of this briefly. So it comes equipped with a Z mod 4 grading. This Z mod 4 becomes a Z mod 2 grading if sorry, for SO3, for the case of SO3 bundles. So I'll come to that in a moment, but really what you should think of is SU2 homomorphisms with certain additional conditions that tell you what SO3 representations you're looking at. And in that case, you'd drop down to Z mod 2. But regardless, in either case, you can still always talk about the Euler characteristic. And this is a result by Chris Caduto that the Euler characteristic of the instant-on Floer homology for a three-manifold is the size of the first homology if it's a rational homology sphere, and it's zero otherwise. So you're supposed to think of related to HF hat of your three manifold coming from Heegard flow theory, right? And or I guess HM tilde coming from monopole flow theory, but there's no version of I minus, or well, not a completely functorial version at any rate. And so we'll only be sticking with this, and comparing it to HF hat when convenient. Yeah. We have our usual sort of functoriality for this Floer theory, which goes as follows. If you have a cobordism that goes from a three-manifold and a link to another three-manifold and a link, through a surface, then you have a morphism between these instanton Floer groups, and it is homogeneous with respect to the Z mod 4 grading. Yeah. Or Z mod 2, depending on context. But in either case, it is homogeneous. And I just want to clarify that there are no restrictions on what S can be and L or L minus or L plus how to be. S could be non-orientable, L minus could be empty, L plus non-empty. All of that is allowed. Yeah. But for the most part, for the cases we'll be dealing with, these four manifolds and the surfaces inside them will be relatively simple. Yeah. Let me just pause for any quick questions about just this very introductory material in case. Yeah. Okay. If there are no questions, I'll keep moving forward. So just to tie it back to Heegard-Floer theory, there's a conjecture by Kronheimer and Mrovka that I sharp with complex coefficients is isomorphic to HF hat, which is the Heegard-Floer analog of your three-manifold with complex coefficients as Z mod 2 graded vector spaces. Yeah. And there's been a lot of progress that's been made on this conjecture, but in its full generality, it still remains open. And what I want to talk about today is about how one computes this, like an additional computational tool that we can use to get more information about this for not necessarily characteristic zero, but for other characteristic fields as well. Yeah. And to start this off, I want to first go over a result due to Floer about surgery exact triangles to sort of set the stage for this. So just to state the result is as follows. So suppose you have your three-manifold and K is a knot inside it. So we don't need K to be rationally null homologous or null homotopic or anything of that sort. But what we do want is a framing. And so this doesn't need to be the cipher framing either. You can use any sort of framing. So with that data, then we can relate the instanton homology of these three manifolds. There is a small bit of decoration that gets in there, but otherwise, the Floer's result can be summarized as just saying that this is an exact triangle of Z modules. Yeah. And to contrast, my result says that if you have, again, in the same setup, you have your frame knot, then you can relate the zero surgery and the +2 surgery, except this time the guy in the third spot is a knot instanton homology. Yeah. So I'll describe what these maps are. These maps will turn out to be linear combinations of cobordism maps. And so they will all be homogeneous with respect to the Z mod 4 grading, but with some grading shifts. But there's some decoration data that goes in. So really you should think of this as for most, yeah. And these are always Z mod 2 homogeneous. Sometimes if you're careful with your Z mod 4 gradings, then you can make it Z mod 4 homogeneous as well. And yeah. So I'll then explain how we can use this to get some simple computations right from the algebra without having to, use anything about the geometric information about these maps, but just the formal properties. But before I move on to that, any questions about either this, about this theorem or Floer's theorem or anything?
The total degree in the exact triangle is still
still minus one.
minus one. Okay.
4. Yeah, just like in Floer's exact triangle.
Mm-hmm.
Yeah. But the computation goes a little differently because these cobordisms now involve some singular surfaces, but there is a similar index formula, and yeah, it's very similar in that front. Okay, so want to talk about few examples. So let's just look at knots and sorry, one sec. There's sorry about that. Um, yeah, so we can consider this triangle for our ambient manifold being S3, and you're looking at knots inside S3, but we don't need to choose the ciphered framing. So say we choose some framing n over here can be any integer. Yeah. And then the n plus 2 and the knot homology are related in this way. And we can pin down what the grading is, mod 4, in this situation. So when n is strictly greater than 0, the degree of this map and this map are both 0 mod 4, and this is degree 3. Yeah. And yeah, so sorry, I don't think this is too relevant. And so one can sort of look at this. We can compute this when k equals the unknot, and this is just z direct sum z and grading 0 to mod 4. Yeah. And this just comes from looking at the actual the critical locus and then perturbing it to be more spot, and then you get this by hand. Yeah. And we can use this to compute the instanton homology of length spaces. So we get this sort of computation with your yeah, with the Z mod 4 grading. I and yeah, I want to clarify that these computations themselves are not new, but what is new is that you once you do this one computation, which is much simpler, then you can already get all of this. Whereas in the earlier proofs of this result in the literature, you had to do a much more complicated index computation to see how many are there in the degree 0 and the uh, degree 2 part, mod 4. So these results themselves are not new, but it's just that the computational efficiency is what I want to illustrate with this triangle. Um, any questions about either of these computations or about, I guess, any other computations? Anything? Okay. Very good. I'll move on to the next situation where we'll do this computation for k being a non-trivial knot. And but before I move on to that, I just want to bring up a bit of terminology. So we have a notion of L spaces in Heegard-Fleur theory and in monopole Fleur theory. In both of these, what this typically means is that there's like the homology of the Fleur homology of your dream manifold looks the same as if there were no irreducible solutions. And what this formally means is that your dimension of whatever flow group you're looking at is the Euler characteristic itself. Yeah. And so what I've been able to show is that the Poincare homology sphere with integer coefficients, its instanton homology has some two torsion. And in particular, this is not an L space with F2 coefficients. So in sharp contrast with Heegard-Fleur theory or monopole Fleur theory. Yeah. So I just want to, I guess, revisit this one point and just add here that C can't be with F2 here. Yeah. And
what happens if you reverse orientation on Poincare homology sphere?
oh, there's a duality sort of pairing that happens. I think the on the mod 4 grading, I think there's like a grading shift of +2 that happens. So maybe it's like if you look, so this uh, result is with Z mod 4 grading. If you wanted it for the reversed one, this will be like Z with in mod 2 grading, and then this will be distributed, I guess, in 3 mod 4.
Okay.
Like this G over here actually is with Z mod 2 grading. This one is in 0 mod 4, but this one is distributed in 1 and 3 mod 4. So they move around a little. But yeah, I mean, this is, yeah. But this is exactly the sort of duality pairing that you get by changing the sign of your Morse function. There's nothing too
Okay.
sophisticated going on. And I just want to point out one other thing that comes out of the falls out of the proof of this, which is that for the +3 surgery, we're able to say that the torsion, if there is any, has to be two torsion. So this is two torsion in the sense of group theory. And over here as well, your two torsion is in the sense of group theory. So some power of two kills your finite group. Okay. But unfortunately, I'm not able to say anything about whether the +3 surgery does it not have torsion or does it have torsion. All I'm able to say is that it has to be two torsion if there is any. Yeah. And I want to contrast this with known results that about these spaces that were known earlier. One is, so P here is the Poincare homology sphere. And this is a result by Chris Caduto that its instant on homology is your field K, is just your field K whenever your field is not characteristic to. So we already knew that if there was any torsion, it had to be two torsion. And this result should be seen as confirming that there is in fact some torsion. Yeah. And I also want to mention that for, sorry, this is a typo. For rational coefficients, this instant on homology for the +3 surgery on the right-hand tetrafoil was already known to be three-dimensional. Okay. What we're confirming here is that that if there is any torsion, it has to be two torsion. But prior to this, I don't believe there was anything known about the torsion at all. Like, is there any torsion? Could there be three torsion and so forth? And now we're able to confirm that if there is torsion, it has to be two torsion. But unfortunately, more, some more computation is required to actually confirm or deny whether there is any torsion. Yeah. Yeah. And I want to mention another sort of more topological reason about why we should care about L spaces in the instant on context. So if you have, this is a result by Baldwin and Sebeck, and it states that if Y is a rational homology sphere such that all your SU2 representations are reducible, then under a certain mild condition on the fundamental group, Y is an instant on L space with respect to K for all fields K. So in a sense, what you can think of this result is that uh, instant on homology does, in some sense, recognize that the Poincare homology sphere's fundamental group admits an irreducible SU2 representation. So just to recall, this is a quotient of SU2 by a finite group. And so that finite group is an irreducible representation. The only other one is obtained by mirroring this, essentially. And while with rational coefficients or with any field whose characteristic is not 2, you might not see this representation showing up. It shows up if you use F2. Yeah. And yeah. Any questions about, yeah, this L spaces or the statements of these results? Oh, we're all good, then keep moving. So let me first explain how one arrives at these both results from the triangle without appealing to anything beyond the formal properties. And then I'll get to the proof of the triangle itself. Okay. So what we want to do is we want to understand all of these, finite, all of these abelian groups, and this is the right-handed trefoil. You want to just look at plus k surgeries. So I just want to mention that since this is an L space knot, we already know with rational coefficients, again due to Baldwin and Speck's results, that the plus n surgery will have dimension n. Yeah. So so we already know that with rational coefficients, but what we want to know is get further. We want to check what it is with integer coefficients. And for that, what we would want to first know is what this knot group is. And for this situation, there's a result of Trondheim-Rovka that we'll use, which shows that there's a spectral sequence from the unreduced Koano homology. Maybe I should write that. Unreduced Koano homology to a I-sharp, like this instant-on knot homology for your knot in S3. And this spectral sequence collapses over rationals and over F2 for quasi-alternating knots, and specifically for alternating knots as well. And so for the trefoil, you can actually compute this by hand and confirm that there's no weird extension issues that show up. And this instant-on homology is just the same as the Koano homology of the mirror, but with some changes in the grading, like the Mas, I guess, yeah, Maslow and quantum grading for the quantum homology combine linearly to give you the Maslow grading on instant-on homology. Okay. And there's a little bit of checking to be done with, the spectral sequence and extensions and whatnot, but this is the final upshot. Okay. And I don't think I need this. Yeah, but let's just stay there. But yeah, I just want to point out that the +3 surgery, it has a very explicit fundamental group as well. And so one could try understanding its instant on Floer homology, right, by understanding the character variety and seeing what AHD connections are there. But that's somewhat more challenging. So instead, what we can do is we can go to +5 surgery and look at this lens space. And for lens spaces, one can actually, again, compute explicitly what the instant-on homology is. This is not covered by the previous sample computation that I did, but one could still like do some index computations and confirm that there are no trajectories in the character variety. And so one arrives at this result. This is with integer coefficients, and this I should mention is with Z mod 2 grading. Trying to figure out the Z mod 4 grading is, yeah, it takes a little bit more work, and at the end, it doesn't give you too much. So I've just resorted to this situation. And then you plug this into the triangle. You have your grading shifts with respect to the Z mod 2 grading. And from here, you're essentially able to, with this information, you're able to conclude that it looks like something like this. and then there is some torsion in the odd piece, and you plug it back in into this triangle, and you still need this fact that A1 is rank 1. And from there, you're able to conclude that even if A3 did not have torsion, A1 did. And again, just to remind you, AIs are all of these abelian groups. And so at this stage, you're able to conclude, okay, A1 has some torsion. And then you appeal to Scotuto's earlier result that if there's any torsion, it has to be two torsion to conclude that this has some non-trivial two torsion. And then you're able to push that on to say that A3 must have had two torsion as well. It could not have had any other sort of torsion. Yeah. So all of this comes from purely formal properties and some commutative algebra. There's no real geometry that goes into like getting this result. If one would say want to improve this corollary to say whether this happens or not, then one would need to look at this space and look at the character variety for that. It's much harder to compute these maps between these flow groups. And so I think it's easy. Like if one wants to improve that corollary, one would need to look at this character variety. Yeah. Any questions about, yeah, anything so far? Okay. So I will now move on to the proof of the actual result itself. And this involves the Atiyah-Fleur perspective, or is motivated rather by the Atiyah-Fleur conjecture. And so I'll explain what that is and briefly, and then move on to how one uses it in this specific scenario. So what we want to do is we want to look at a Hegat splitting of our three manifold. And so say H1 and H2 are G handle bodies, and then sigma is a genus G surface. And we look at the moduli of flat connections, flat SU2 connections on your surface and on your handle bodies. Yeah. So just some facts that this is a symplectic manifold of real dimension 6G minus 6. You need G greater than or equal to 2 here. And it is symplectic on its smooth locus. And the handle bodies give you Lagrangian immersions in this symplectic manifold. Yeah. And under this assumption, the Atiyah-Fleur conjecture just states that a flavor of instanton homology is isomorphic to Lagrangian Fleur homology of these two Lagrangians inside your symplectic manifold. Now, what we'll do is we'll try to go beyond the original context of the conjecture. So in the original conjecture, you needed these to be handle bodies and to be your and you needed these to be handle bodies. You needed this to be genus greater than or equal to 2. And instead, we'll dispense with all of that. And just to form a heuristic, we'll go to the case where this genus is 1. Only one of these two is a handle bodies. And yeah, we'll see where that gets us. And there's more work to be done to convert it into an actual proof. But I just want to give you a heuristic idea as to how one could have seen the original result that was stated to begin with. Yeah. Okay. So, like I said, we'll dispense with the restrictions and look at the situation. So you have a knot, and this is a frame knot. And so that gives us a decomposition of your three manifold into the knot complement and the knot itself glued along a two torus. And the gluing data is given by this framing, essentially. And I now recall that the moduli of flat connections on two torus, when you mod out by conjugation, is the pillowcase. So the pillowcase is topologically S2 with four singular points. These four singular points are over here, and this is your S2. And these purple lines that you see here are the Lagrangians, purple and blue. So the blue line corresponds to the knot complement, and the purple lines correspond to different surgery coefficients that one could have used. So if you use this situation, this corresponds to infinity surgery. You could have used this, which corresponds to zero surgery with some non-trivial W2, or this one that corresponds to +1 surgery. Yeah. And I want to point out that in the context of Fleur's original triangle, you have infinity surgery, one surgery, and then zero surgery with some decoration. And these three sort of fit here together in the sense that if you take a connect sum of any two of them, you get the third one up to Hamiltonian isotopy. And this is what's going to be important for us. So I want to recall the official result from symplectic geometry. This is due to there are various versions of this, and uh, one of the versions is by Fukaya, Ota, Ono, and a very similar version is also due to Seidel. And in the simplified context, at least what we're thinking about, we want two Lagrangians that intersect at exactly one point, and they intersect transversely. And let me call that point at the point P. Then you can then given any other Lagrangian L, you can form these flow groups where this is connect some P, and these fit in an exact triangle, and you have some information about what this map is as well. Yeah. And yeah. And what this immediately, like for instance, for Fleur's triangle immediately follows from this situation, from this figure. And similarly, in my context, what we have is we have, say, zero surgery with no decorations. You have +2 surgery, and then you have this meridional loop that corresponds to your the Lagrangian corresponding to the traceless condition. And so this gives you the not Instanton homology, and the zero and +2 surgery are the other two slots that you get. Yeah. Any questions about either this pillowcase picture uh, in either like Fleur's original case or in this situation?
What do you mean by immediately follows from?
Oh, immediately as in, sorry. What I meant is that these Lagrangians, they satisfy, like one of them is L0, one of them is L1, the other one is the connect sum. And
Yes.
so if you take your other Lagrangian L to correspond to your knot complement, then these, and you believe in the Atiyah-Fleur conjecture, then
Oh, okay. If I believe in the conjecture, okay.
sorry, yeah, I
Yeah,
mean,
then
heuristic,
definitely immediately
yeah,
follows, yes.
yeah, I'm sorry, heuristically, this is
Okay,
not proof. Yeah, yeah. But
got
the
it.
point is, this information actually can be converted to tell you what the morphism is. So over here, you can write down this four manifold, and that is related to the point P of intersection. And similarly, one can essentially guess what these morphisms are as well. And Fleur's original proof actually, like what it consists of, is once he gets all of these guesses from this sort of result, then he uses he uses ideas of even the proof of this to show his triangle. And yeah, so what I meant, yeah, I was a little being a little careless with my wording. But what I meant is that if this conjecture, like while it's stated for this three manifold, the expectation is that there's some level of functoriality in this isomorphism as well. And if you use that with the explicit maps that you get here, then you can guess what the maps are over here, and then you can run the proof purely in the instant on land to see that this expected result is true as well, bypassing either proving this or proving that. But yeah, but the maps, the groups, everything comes from this perspective. And similarly over here as well. So, for instance, yeah, you have this map psi that corresponds to looking at these both. Now, these both intersect at two different points. So you expect psi to be a linear combination of the morphisms corresponding to these both points. And these ones are much simpler because this loop intersects this one at only one point, intersects this one also at exactly one point. And so there isn't too much ambiguity about figuring these out. But for figuring psi out, you need to decide whether you want to add these up or do you want to subtract them, right? So this result doesn't tell you anything about how this should be added. Like, is there a plus sign? Is there a minus sign? Is there some canonical sign that depends on some other data? But yeah. So one has to figure that out, and one can figure out what what combination works and what the appropriate four manifolds are as well. And the result is the following. So if you if you look at your elementary two-handle attachment with say framing 2 or framing 0, you get these four manifolds from Y to +2 surgery and 0 surgery. Then these maps can be described as, for this one, you reverse this cobordism and you keep track of the core that you attached. So pictorially, this looks something like um, you have your two handle that you attached and you add this information to the cobordism so that it starts from Y2 and then goes to this situation where this is your knot. And for this one, it's very similar. You look at the zero trace of the 0 surgery, and then you look at your core. Yeah. And your map psi is a linear combination of two different four manifolds, one with some decoration. And this four manifold can be represented by a relative Kirby diagram. So if this is your knot with some framing, then uh, sorry, this is your knot K with framing 0, then the relative Kirby diagram looks like you have this meridian with -1 framing, and then you add on top of that another meridian with -2 framing, and that's your four manifold. And there's a decoration that you also need to use, which corresponds to this one. And yeah, I mean, figuring out what this map psi is under all of these identifications takes a little more trial and error, but this is what the final result ends up being. So yeah, again, Nikolai, I guess, corrected me that this itself is not a proof. This is more of a heuristic, and you can guess all these maps. But then for the actual proof itself, there's the triangle detection lemma of Oshwat and Szabo that one can use. And there's a slight upgraded version of this triangle as well that's true. And for that upgraded version, the Oshwat-Szabo triangle detection lemma falls short. But there's another triangle detection lemma due to Francesco Lin, and we can use that to get an upgraded version of this with some local coefficients as well. But yeah, but this heuristic is very central in trying to figure out what maps fit in this triangle and what the triangle must be. Yeah. So any questions about this heuristic or how it applies in this situation? Um, okay. If there are no questions, since I have a little more time, let me explain so there's some recent developments on the Heegard-Floer side about analogs of this as well. And since I have more time, let me just explain some of that. So, so I want to recall first some known results in Heegard-Floer theory that are somewhat similar to this. This is U2 Bushwath and Szabo. And okay, let's see. I think that's the correct accents. So if yeah, I think they've proven this in slight more generality than what I'm writing down here, but that takes a more complicated form. So let me just state this simplest version. So this and y a with y a rational homology sphere. And now, since this is a rational homology sphere, K is rationally non-homologous, and so it gets a framing from it. Or no, so you know what? And let me also just add K is Z null homologous. Yeah. And then you have this triangle between where I'm using the Seifert framing, f hat of y and plus 2k and f hat of y direct sum hf hat of y. Yeah. So in this situation, if you're going from n surgery to n plus 2 surgery, then this map is not related to the map that we have, but this overall triangle is stays completely within the realm of three manifolds, and you get two copies of your infinity surgery homology rather than a not homology. Yeah. So this was known, and the project started with maybe trying to prove this again in the Instanton world, and that didn't happen. Instead, this was replaced by some not version. Now, what I want to mention is that there is a version of not homology in Heegard-Floer theory. So this is not this the analog of I sharp of y comma k. This is should be thought of as a reduced invariant, like a reduced homology, and this is unreduced. So there is a reduced version in instanton of for not homology in instanton Floer theory as well. This is denoted by I natural of y comma k, and this is reduced. And it is expected that these agree with each other for complex coefficients, but not this one, right? So there's this issue that there was in Heegard-Floer theory that there is no unreduced analog of the Heegard-Floer knot homology. But this has been rectified very recently, in fact, in January, that I guess, uh, let me write this as a definition. And this is by Yihun Nam. And what he has come up with, he dubs it HFK prime of y comma k and unreduced not invariant. And with this definition, he's been able to show that an analog of my triangle, like this triangle, also holds in Heegard-Floer theory. Yeah. I don't know too much about uh, this definition, but basically, it these both agree for say the unknot, and at least for the unknot they do agree. So for the unknot, I just want to point out this is isomorphic to Z, this is isomorphic to Z direct sum Z, and this is isomorphic to F, where F is Z mod 2. And for the unknot, this gives you F direct sum F. So these do the right thing, and like since you have a similar triangle, one expects that this is perhaps the right version of this. But again, I think, uh, yeah, I think even for the trefoil, this with F2 coefficients differs from this with F2 coefficients. So
By the unknot, you mean unknot in S3?
yes, I'm sorry, I mean unknot in S3. Yes.
Mhm.
Yeah, for all of these, I meant unknot in S3. So yeah, for that, all of these agree with, complex numbers or F2 or whatever, but these both, I think, disagree with F2 coefficients for the trefoil already. And so, yeah, again, if these are supposed to be, and if you expect them to be equal, you expect them only over characteristic zero fields, not over F2 or something else. Yeah. And yeah, I think with that, I will end my talk here. Thank you for listening.
Yeah.
Okay, well, are there further questions?
Are there any computations of this unreduced Heegard-Floer theory to compare?
Of this unreduced guy,
Yeah, you were. I think you were saying that that should compare to the unreduced.
yeah, like these both should be compared to one another, but I don't know if there are many computations of this. This paper by Gi Hyun Nam, who's a graduate student at Princeton,
Uh-huh.
it came out only in January, and this
Yeah.
January this year, and I haven't spoken to him about it. And I think maybe there's a couple computations over there, like in his paper, but I don't know if he goes anywhere beyond like homologically thin knots, like homologically thin with respect to Quano homology. And for that, I think the point is that, like, at least over here, it agrees with the Quano homology just because of the spectral sequence collapsing. And I think, if I'm not wrong, I think there's like a spectral sequence by Batson Seed, if I'm not wrong, about from Quano homology to Heegard-Floer, and maybe there's some version of that that tells you something about this for thin knots, but I'm not too certain. I'm not pored over the paper too thoroughly to tell you too much. But yeah, I mean, I guess for credence as to why one might expect these to be related is it agrees for the unknot and this triangle is the same. So if you go with the fact that this agrees with Heegard-Floer for complex coefficients, then one could think that maybe this map was the same. And Gideon does say that his construction, like of this triangle in this theory, is motivated by the specific maps that I've used. But again, like at the end of the day, he gives some map algebraically, and I've not tried comparing if it matches up with a cobordism map, and if it does, should it be equivalent to this cobordism or not? So yeah, but I guess the point is, since we don't have any better candidate, then we can just ask whether these both are equivalent.
Yeah, makes sense.
Yeah, it's yeah.
May I ask a question about your calculation for Poincare homology sphere?
Yeah. Let me
Uh,
bring that page
yeah.
up. Yeah.
Yeah, it was in the beginning somewhere.
Yeah.
Yeah. So if you were to compute I sharp of sigma 235 from Chern-Simons theory directly,
Mhm.
the critical points of Chern-Simons would be several circles, right?
So over here, you didn't conjugate by the SU2 action. So the framed character variety,
Uh-huh.
the Poincare homology sphere, looks like there's one SO3, and
Yes, that's right.
yeah, because the stabilizers are Z mod 2s, and so there's these both, which is the sort of defining representation, and it's sort of mirror in a sense, and then this is the trivial representation. So this is the character variety, and you can perturb your Chern-Simons function to make sure that these are more spot. That's achievable. And then yeah, but I think it's much harder to actually. So here's the scope of the difficulty. So I think in Fintushel and Stern's paper, where they've figured out the instanton homology of ciphered fibered spaces, they look at the thing where you conjugate by the SU2 action, right?
Yes.
And they do an index computation that confirms that the index is always even. And at that stage, they're able to just say that the differentials vanish. Here, the problematic thing is if you, for instance, yeah, look at the Morse-Bot spectral sequence sort of thing, then you have all of these SO3s, they uh, can be written as like, uh, well, sorry. Hmm. So each of these SO3s should be seen as like a four-term complex. So there's like copies of Z and there's like some maps between them. And you want to now see how these different critical points interact with one another. And the point is that you could have, say, this cell, like the top cell, interacting with the bottom cell over there. This is a degree 4 change. So you're looking at AHD connections of index 4. And these moduli spaces are indeed non-empty. I think like me, I don't believe if Intuition and Stone themselves did this computation in simple examples, or if somebody else did, but there are non-empty four-dimensional moduli spaces possible. And then you need to compute, is this map zero, non-zero, or what it is.
I
And
think Kronheimer found the moduli spaces, in not looking to do it as in terms of
right.
theory, but sort of before that
Okay.
early work.
Yeah. I'm forgetting my references. I think like some algebraic geometers also worked on this. And yeah, but okay. Yeah. I mean,
The moduli spaces are known generally.
yeah, but you need something more than that because you need to actually evaluate them by one of these new classes. Like I think you need to evaluate this by, so you're looking at R cross P, you're looking at its moduli space, and you want to pair this with the new class of a point. And you want to compute what this integer is, because in a sense you can think of my result as confirming that this should be some power of 2. This is not quite correct on the nose, but you need to write down the full complex and then you need to see which one the parity, or which one like being a power of 2 or not being divisible by 2 matters. Sorry, yeah, I don't, yeah. And you need to do more to like actually find out what the homology is. Like if you're working rationally, all you need to know is whether this is non-zero or not. But if you're working over, say, f2, then you need to know whether it's divisible by 2 or not. And if you're working over integers, you need to know what it is as an integer.
I think a lot of this was done for equivariant instanton homology. But for equivariant, you get like isolated points from the irreducibles, but then you get the big one from the irreducible. So it's like the other way around.
Oh, right. So I should clarify that so what you're describing is closer to, yeah, it's closer to taking the equivariant
Yeah.
homology of the character variety. But this is what I wanted to look at was just forget the SU2 quotient, like just look at
Yeah.
SU2 character varieties and look at this. But so you should think of this as how, so HF hat, right, can be, or at least at the level of complexes, this can be seen as CF minus tensor FU mod U. And this U action is coming from, homology of BS1, because this is like, if you compare with monopole Floer theory, for example, like Higard Floer ought to be like a S1 equivariant uh, uh, gauge theory, I guess. And so this is the full equivariant thing. This is the full equivariant version, and then you sort of take this tensor thing to get the complex of the framed guy. And so something like that is also afoot here. It's just the theory for equivariant instanton homology is not as well developed. So I just stuck to this incarnation directly rather than doing something algebraic of this form. But I think like Mike Miller's thesis has the sort of formalism that makes an analogous formula true for instantons as well. So something like C I sharp, I guess, is, so he develops an invariant like Ci minus, and then you want to tensor that by, I think he maybe develops it over rationals, and you're looking at this. So that is true. It's just instead of trying to compute this invariant, you can directly compute this thing. Yeah. But they are related. But another thing is, I can't remember if Mike Miller's thesis works over integers or not, because at some stage yeah, because I think he is really secretly working with um, BSO3, which differs over F2 and over rationals. So if you want this picture integrally, you might need to work harder than this sort of formula. So yeah,
Yes, thank you.
but yeah, that said, I've not tried thinking too much about whether this interpretation gives you any upper hand for this computation.
I think they are similar, but they are different.
Yeah, it's and different in a subtle way, I guess.
Can I ask what is the expectation for the two torsion group then from the picture above? You get a Zima2 you get two copies of Zima2 from the degree one? No, from the picture you
So
just
I
said.
think so this is something I had a few conversations with Mike Miller and Chris Caruto about, and I think they expect that, like, they expect this to be, I think this map to be one, I believe, and this map to be, I think it's expected to be a power of two. And so what happens? Let's see. So this is these both die, and then this remains. And over F2, what would happen is these both still die, but then I think it's going to be 7-dimensional with respect to F2 coefficients.
Sorry, I was just thinking with over Z.
Yeah. So
Over Z, you have a Zima2 in degree one. on both sides, like the second.
Right. So, so just to confirm, you're asking about instanton homology of the Poincare homology sphere
With
specific.
Z.
Okay.
Yes, yes, yes.
Yeah. So I think so. I told you that with the canonical Z mod 2 grading that you have, it's something like this, and I expect G to be isomorphic to something like maybe I think the expectation is that this is 4, and so there should be, I guess, Z mod 2 direct sum Z mod 2 direct sum Z mod 4,
Okay.
something like this, I suppose.
Yeah, that
Yeah.
makes sense. Okay.
Yeah, but again, I think like in these computations that they did, there were some caveats, and yeah, I don't think they've gotten around to actually writing this up anywhere. So, take this with a grain of salt.
Yeah, it's good to know what you expect. Yeah.
Yeah.